Hello, and welcome to a video whose title and thumbnail practically invite a comments section that's going to be several pages of, well actually, what about? So allow me to preempt that with the observation that there are in fact a whole load of open source recreations of classic games. OpenTTD, OpenRCT2, OpenLoco, Exalt, ScumVM, the last of which is of course a recreation not of one engine, but of dozens. But why aren't there even more? Where's the open source Gran Turismo 2, the open source Stunt Car Racer, the open source Frontier, the open source Captain Amphibio's 3D frog arranging simulator? Now before you at me with mentions of Pioneer or V-Drift, I'm not talking about projects inspired by or attempting to build ground-up reimaginings of original games. I'm talking about one-to-one recreations which load the original data files, display the original graphics, and replicate exactly the original gameplay, maybe with the odd enhancement thrown in here or there. Well, I didn't want to just sit here moaning about the situation, so instead I decided to try making my own. But first, we need to talk about Test Drive 3. Test Drives 1 and 2 were the product of a cosy relationship between Distinctive Software, or DSI, and Accolade. DSI would build these classic scalar-style sprite-based racing games, and Accolade would publish them, which all worked fine, until Sega contracted DSI to produce a DOS port of Outrun, to which DSI thought, we already have code for doing scalar-style sprite-based racing games, why don't we use that? Accolade were rather miffed at the Test Drive 2 code they'd paid for being used in a non-Accolade game. DSI have mugged us right off. They probably didn't say, Accolade not being based in East London. The resulting lawsuit judged that Accolade had not, in fact, been mugged off, but did leave them with the rights to make further Test Drive games, and without a partnership with DSI. So DSI went off to make 4D sports driving / stunts. For more about that story, I refer you to my good colleague Dudley of Yesterzine. In the world of Test Drives without DSI, Accolade got Tom Lowry to build their own fully 3D engine to power Test Drive 3, The Passion, and later Grand Prix Unlimited. Test Drive 3 is very ambitious for 1990. It's also very flawed. Whatever passion the title refers to, it's certainly not a passion for handling a wide range of hardware specifications. The game engine features neither code to make it run at a consistent frame rate, nor code to adjust the rate of simulation to compensate for the game running at faster or slower frame rates, which leaves you with two options. One, run it on a low-end 386 and have a game which is fairly playable, but runs at a painfully low, vintage-correct frame rate. Two, run it on a 486 or faster and have a game which features a decent frame rate, but runs unplayably fast. Now, the rest of YouTube has covered this in great detail and made the region-specific pains noises of at least 3 different countries. But this is Timberwolf stuff, and you know what we do differently here. Creatively mispronounce the names of developers and the hardware they programmed on without explanation or apology. No, wait. The other thing. Find any excuse to reference x86 assembler. Allow me to explain why Test Drive 3 runs so inconsistently. This is a program I wrote which displays a very crude DOS version of the DVD screensaver. Here it is running on a 286, and here it is running on a 486. Same speed, exactly what you'd expect from any program written since the only CPU available was a 4.77 MHz 8088. The reason is this code here. Before drawing the next frame, it sets this variable canDrawNext to 0. When it's finished drawing, it waits in a loop until canDrawNext is set to 1. But wait, you don't say because nobody's really watching this for the badly written x86 assembler content. Is that not an infinite loop? It would be, except for a feature of low-level computing called the interrupt. An interrupt is something that says, when this thing happens, run a particular piece of code. The thing which happens can be something external like keyboard input, or something internal like a divide by zero error. Or it could be, of particular relevance to us here, the system clock ticking. The code which runs in response to an interrupt, or interrupt service routine, can be customized. On the PC, we have an interrupt vector table taking up the first kilobyte of memory, which tells the computer for each possible interrupt where the code to handle it is located. If I'm an utter sociopath, I can read and write to that directly, but DOS also provides functions to do this, using its own interrupt, int21h. Think of int21hex as the Swiss Army knife of DOS programming. So using this, I set two interrupt handlers of my own, one for keyboard input so I can exit when a key is pressed, and one to execute every timer interrupt. And if we take a look at that latter, you can see right here that I set canDrawNext to 1, so when I return control to my end of drawing loop, it will finally move on. But wait, I'm not done with irrelevant detail yet. By default, the 8253 timer in the PC generates an interrupt 18.2 times per second. This is a great frame rate if you want period correct detail, but it's not so great if you want, playability. So I also tell the timer, hey, rather than ticking 65536 times before generating those interrupts, how about only 32768? This now gives 36.4 interrupts per second. Which is great and all, but the interrupt I'm messing around with also controls updating the system clock. So I need to call the original timer interrupt service routine, and even better, only do it every other time my interrupt service routine runs to prevent time running at double the speed. Yay! Remember when this channel just pointed and laughed at Alex Kidd games? But what happens if I remove that delay loop? Now, it runs like this on a 286, and like this on a 486. Exactly what's happening in Test Drive 3. With no delay loop, I have nothing which compensates for the box taking less time to draw. It goes faster and faster, the more powerful your CPU gets. Exactly the same as Test Drive 3. I never understood why they did this, not least because the intro does have code to wait for the timer, and will run at the correct speed, even on a high-end Pentium. It's not even an accidental bug. Grand Prix Unlimited has the same problem, and by the time that came out, there were CPUs more than fast enough to render the game unplayable. Did Accolade refuse to buy Tom anything faster than a 286? One possible reason is that the Test Drive 3 engine already uses the timer interrupt to load the next few milliseconds of music and sound data into your audio device of choice. It's possible that Tom didn't want to mess around making the music code and calling the original timer ISR correctly handle a much faster interrupt rate, or that this was a lot of complexity when most computers would struggle to maintain even the 18.2 times per second of the default timer. It's still feasible they expected the majority of players to be able to slow things down acceptably by turning the detail up. While I'd say CPUs capable of rendering these games unplayable existed in 1990 and 1992, they were still outrageously expensive, and thus far from common. Whatever the reason, I was left with an idea. Why not reverse engineer Test Drive 3 and see if I could insert some kind of delay loop, or possibly even a mechanism for scaling the physics calculations? Getting back to the title of this video, reverse engineering is intrinsically bound with creating one-to-one open source implementations of a game. While you could slowly try to guess your way around how the file formats work and what the gameplay logic is, to recreate a whole game engine that way would be a long, painful, and often inaccurate process compared to just looking at the code. And while it may be a little bit of a legal grey area, no game this old will have an end-user license agreement saying you can't reverse engineer it. So long as you don't distribute the files, and what eventually ends up in GitHub is a cleanroom implementation that doesn't directly use any of the original code, you're probably okay. Note, I am not a lawyer and this does not represent legal advice. Please do not get in trouble for recreating 1990s game engines. While the discipline of reverse engineering covers everything from poking at the data files to running the game in a debugger, there's one very specific form of reverse engineering we're interested in here: disassembly. Disassembly means taking the bytes of the program code and turning them back into assembly language instructions. And to explain why this is both possible to do and yet almost impossible to do well, I need to explain a little bit about how an x86 CPU works. The x86 architecture uses the same memory to store both data and instructions. If you look at what's in RAM at the point your program is running, it's a bunch of bytes. The CPU has a special register called the instruction pointer. This points to a particular location in memory and says, I'm going to execute this next. Take a simple assembly language instruction like move BL AH. This copies the upper 8 bits of the 16-bit AX register to the lower bits of the BX register. You don't really need to care about that. It does things. In memory, this instruction is represented as a series of bytes, 8A or 138 for a move instruction, with two 8-bit operands, followed by D and C to indicate BL and AH as the operands. Because we're dealing with registers, each operand can be represented using a single 4-bit nibble. So when the CPU comes to execute this instruction, it'll fetch those bytes and then increment the instruction pointer to the next instruction. We've also got instructions like jump and call to directly manipulate the instruction pointer, so we can have loops and logic, rather than a program which executes every instruction in order exactly once, then quits. If we're trying to disassemble a program, we can take those bytes and say, aha, that is a move BLAH. Except we might not always be correct. Let's say our program also has some constants for data, and one of those constants is 138. When we encounter this in the program's executable file, how do we know whether this is the start of a move instruction or just the value 138? There's absolutely no distinction in an x86 program. There are no special bytes to say, this bit's data, this bit's code. If you want to, you can jump straight into the middle of your own data and start executing it as code like, well, probably the same kind of sociopath who writes the interrupt vector table directly. It is literally possible to have a program which loads its own code from a BMP file, in case you ever fancied writing machine code in MS Paint. In fact, here is the bouncing square program you just saw as a BMP file. Note how much space the array to hold the screen buffer takes up, compared to the actual program. This isn't even the most ridiculous thing you can do with your own code. Because instructions are multiple bytes long, and yet you can jump to single byte precision, you can start executing code from the middle of an instruction. This tends to go badly, because it's very unlikely this is a useful or sensible sequence of instructions for the CPU to execute. But since they're valid instructions, it means you can't just start disassembling any old sequence of bytes, because you have no idea whether you have the program you're looking for, or some complete nonsense, because you're off by a single byte. So a typical disassembler will look for the starting point of a program, and disassemble all of the bytes as code until it finds a ret, or return statement. If it finds a jump or call, it'll follow that and continue the process until every accessible line of code has been explored. Anything left, it will assume to be data. This will give us what looks like an assembly language program, but in fact, the odds of it assembling back into a correctly running game are minimal. Let's talk about offsets and data. Somewhere in our program is a big bunch of data. If we want to do some computation on that data, we need to load it into the x86's registers, which can be done in one instruction. Now your assembled executable won't contain the label MyData. It will contain the numerical address of where that location is in the file. So let's say MyData ends up at byte 16384 in our executable. The disassembled code will look like this. A good disassembler is smart enough to figure out that this is a data reference. So it sticks in a label at 4000H, and you get something like this. But what if the code was more convoluted? What if it did something like this? Please do not type this into an assembler, it probably won't assemble. Imagine this is starting to cross the boundaries of function calls, or if the memory address itself is loaded from data. A disassembler isn't going to be able to figure this out. You might be wondering though, since our disassembly is a one-to-one mapping of bytes in the executable file to instructions, surely we could just reassemble and things would be fine, whether we figured out if numbers are references or not. Well, it would be, until we added or removed an instruction. The moment we do this, everything after that point is offset by the number of bytes of that instruction. Memory addresses which previously pointed to the right place might point to something else entirely. If the thing they point to is something called a jump table, a list of code addresses to jump to depending on the value of another variable, that's going to go very wrong. Wrong of the jumping into the middle of an instruction and ending up running a completely different program variety. So you may be thinking, okay then, just avoid changing anything too dramatic. Work slowly backward from the end of the program, and when something breaks, go back and fix anything which looks like it might be a memory address. Here is where x86 really starts rearing its ugly head. While there is a one-to-one mapping from bytes back to instructions, there is not a one-to-one mapping from instructions to bytes. There are multiple ways an assembler can represent the same instruction, with differing lengths. So even if you haven't changed a single thing about your disassembled program, there's a good chance your chosen assembler will reassemble it into something with a different length to the original. None of this is insurmountable, but we've gone from the dream of having a nicely reversed program in x86 assembler that we can hack on and see what happens, to a nightmarish mess of memory references that might not even get as far as switching graphics mode before crashing. Correcting memory references is possible, but to do it, we need to be able to work out whether something is clearly the address of some data, some code, or just a constant. Which means having a good idea of the program's original structure, and having only a small number of possibilities to try before we know for certain what each number represents. You may wonder why the works of Chris Sawyer are disproportionately represented in open source recreations. In fact, every one of Sawyer's major isometric game engines has an open source reimplementation. Well, it's kind of the same engine, extended and updated, especially in the RCT to RCT2 to locomotion case. But aside from the ease of borrowing reverse engineered code from another project, I think this is for two additional reasons. Firstly, they were originally written in x86 assembler, so while you won't get back the macros and variable names Chris would have been looking at on his monitor, you will get something which is very close to the layout of the original source code. When you see a function call, or a jump, it's something Chris originally intended to be, a function call or a jump. For programs written in a higher level language such as C or C++, this is not the case. C compilers aren't intended to produce human readable machine code. They're intended to produce fast and small machine code representations of programs without taking an age to compile them. This means they will add jumps, turn your code into nested functions, and obfuscate even the clearest of intentions. Take almost the simplest C program you can write, and the compiler still produces a huge pile of machine code that sets up error handlers, resizes the stack, and generally makes life hard for the reverse engineer. The second thing about Chris Sawyer's Tycoon games is they were all written for 32-bit platforms, either protected mode DOS or Windows 95. Most 32-bit x86 programs use what's called a linear addressing model. The CPU has 32-bit registers, with memory starting at 0 and ending at a lot of Fs, a contiguous 4 GB range. So we know that when we see a number, it can be one of only two things, a constant or a specific memory address, and most of the time if that number appears in code, it's going to be obvious from the context. But anything which runs on a 286 or earlier is running on a 16-bit processor, with 16-bit registers, which means the registers can only hold values from 0 to FFFF, a range of 64 kilobytes. Since the PC infamously has access to 640 kilobytes of conventional memory in real mode, it raises the question of how this can be when I just gave you a number an order of magnitude off. The solution is an extra set of registers, called segment registers. These are also pointers to memory, but internally every address is multiplied by 16. So 0 by 1 actually points to byte 16, 0 by 2 to byte 32, and so on. To reference a piece of memory at 128k, we'd load 0 by 2000 into the relevant segment register and 0 into the address register, or 1 by FFF into the relevant segment register and 0 by 10 into the address register. Old PCs are complicated, okay? What this complexity means is that when we see a number in a 16-bit DOS program, there are a huge range of possibilities for what it could represent, depending on what value is in the data segment register at the time. In fact, this is trivially easy to reproduce. Create a program with a small memory model, and when it starts, the data segment register will be set not to the data segment, but to an area of memory called the program segment prefix. If you try to access the first few variables you declare, you'll in fact be pointing at memory containing internal details used by DOS, unless you set the segment register yourself. Not that I ran into this several times while building that example program, including trying to load the addresses of the original interrupt service routines from the wrong segment, and losing pretty much an entire evening to wondering why my program was able to crash DOS after it had finished running. Nah, didn't happen. At least, not yesterday. Even better, because segments can be small, and segment registers can be loaded with addresses in the middle of a segment, it's quite possible for small numbers like 0 by 0e to refer to valid memory addresses in a segmented program, whereas that would be very unlikely in a program with linear addressing, especially one where all the data is declared at the end. Oh, and if you're really unlucky, the values in those segment registers might themselves be loaded from references to memory locations, which probably won't be correct thanks to the aforementioned "my program is a different length from what it expects to be" problem. This is almost impossible to identify from static analysis alone. Maybe you could do something with a combination of disassembler and debugger to identify the most likely values for each, but with a notable exception I'll get to later, this isn't something you tend to find in disassembly tools, because they generally target platforms much newer than 16-bit real-mode DOS. Which brings me back to my attempt to reverse engineer Test Drive 3. Test Drive 3 is written in C, compiled using the Microsoft C compiler. It's a 16-bit real-mode DOS program with a segmented memory model. It was also written, as far as I can tell, in a bit of a hurry. There's the occasional telltale sign of just getting this damn thing out the door, such as some routines which find out what interrupt handlers are set by calling the DOS function to return the interrupt table, and some which just YOLO right in and yank the details out of memory directly because why not? All of this conspires to make it a pain to reverse engineer. I know which functions draw the menu and handle keyputs. I know where it plays the painfully short music loops. I know where it loads files and what runs the intro. I even have a vague idea of which variables control the current car rotation and position. But even after several weeks of carefully tweaking disassembled code, I cannot stop it from doing things like deciding to copy the graphics buffer right over the top of the program's own code, and then trying to execute the result. After a month of work, this is, sadly, as far as my reverse engineered version will get. Doubtless given more time, I could identify what's causing various registers to be loaded with the wrong values and spray the contents of the graphics buffer all over the place. But the further I get into the game before seeing the first crash, the slower and more painful this investigation gets. Which seems like where the rest of the internet is at. Sebastian Mac has figured out the file formats enough to load the tracks, and I saw a screenshot where someone had put those into Unreal Engine with a basic buggy prefab to drive on them. But promising as that is, they're still more at the reinterpretation end than the one-to-one open source recreation. And to be brutally frank, other than extracting those maps, Test Drive 3 is not worth it. It's an ambitious and pioneering game for the era. It's a free-roaming game world with multiple routes, weather, AI traffic, police, and 3D polygon graphics throughout. But even if I were to get it running with a decent frame rate, acceptable control sensitivity, and a clock that counts exactly 1 second per second, it's still going to have no real physics to speak of, horrible sound, and music that repeats more frequently than a daytime radio playlist. Yes, an open source recreation would be able to fix all of these things given time, but if you're going to change the game that much, you may as well just write something to load the assets and throw them in Unreal Engine. Which is why there aren't more one-to-one open source recreations of games. It's too much work to painstakingly hack away at the convoluted x86 assembler produced by a combination of compiler and disassembler to get a vintage game engine working, when you could just start again from scratch and create something with reasonably similar gameplay in a much newer game engine, using guesswork and knowledge of vintage techniques to figure out how the file formats work. And that's assuming we're not talking about games recent enough to have end-user license agreements that definitively state, no reverse engineering for you. So there you go. There are indeed some one-to-one open source engine recreations, and many more open source games inspired by classics. But there's a reason there aren't more, and that's because making them is hard work, which requires a lot of knowledge of x86 assembler, how DOS works, and far more patience for staring at a debugger than I have. Even only getting as far as making the intro work has given me newfound respect for the people behind projects such as ScumVM. Except that's not the whole story. I don't want to leave you on a downer ending, and I don't need to. What I've just described is the current situation. There are a couple of things in the works which, if they pay off, will completely obsolete this entire video and ensure that I'm going to spend most of 2024 responding, "This was recorded 2 years ago before that thing existed in its current form," to comments on it. The first is Spice86. This takes the approach that since an emulator executes the machine code as compiled, you could replace any call instructions in there with your own code, and providing it gives the same end result as the original, then the program running in the emulator will never notice. So you can replace functions one by one, rewriting each in Java until one day you look at your project and realise everything is Java and none of it is 16-bit DOS executable. Currently it only works properly with Cryo's Dune, hence the name, and a couple of other games, and due to the nature of that function-by-function approach, the resulting code is reminiscent of very early versions of OpenRCT2. But as OpenRCT2 shows, once you have something which compiles and runs in a high-level language, it's only a matter of time before you have something that's a lot cleaner and easier to read. The second is MASM to C, in combination with a forked version of libdosbox. The MASM to C part provides a series of libraries and a translator program to convert 16-bit x86 assembler to valid if slightly esoteric C++, which can gradually be replaced with less esoteric C++. But the relevant part here is the version of libdosbox, which takes decompiled output and runs it against the original executable to find out where the segments are wrong, or the disassembler incorrectly interpreted code as data, or vice versa. It won't help with code paths that are rarely used unless you know how to reliably trigger them, but in terms of getting a running executable with variables in the right places, these are huge. Now neither are particularly user-friendly at the moment, but I think you'd excuse the authors of both for wanting to get them working and supporting a wide variety of software first, before spending valuable time letting any idiot compile it with whatever operating system happens to fall to hand. Now, getting a running and compiling piece of code you can mess with is only the first step on that long road to creating that clean open source reimplementation. But it is an important one, and making it easier dramatically increases the number of people who are able to spend their free time bringing a game they love back into the modern world, or fixing the 30-year-old flaws of a game that was ambitious, but rubbish. And to bring this to a very appropriate close, not only do these projects offer the tantalising prospect of reverse engineering 16-bit DOS applications becoming much more accessible, but one of the test examples for MASM to C is, of all things, test drive free. So maybe that open source remake is closer than we think. And there's a good chance I'm going to go into YouTube Studio one day soon and find a comment that starts, "Well, actually, what about?" but ends with a link to a GitHub repository containing a fully working copy of Test Drive Free that fixes the low frame rate and problems with faster machines.